Hi there, my name is Raymond Doe, and welcome to my Physics 2211 Lab 5 video on the conservation of momentum and collisions. Hope you enjoy. In this lab, we will observe and attest the physics principles of the conservation of momentum, the demonstration of collisions, and analyzing the motion of objects interacting in inelastic conditions. The purpose of this lab is to computationally prove the transfer of momentum, which is mass times velocity, between objects in collisions. One of the fundamental principles relevant to our experiment today is Newton's second law of motion, also known as the momentum principle, which defines a force to be equal in change in momentum per change in time. This formula can be rewritten to predict final velocity and momentum. This principle also holds that under the conditions of a net force equal to zero, the velocity of an object will remain constant. Thus, the final velocity and momentum would equal the initial velocity and momentum. The key concept that we'll be examining in this experiment is the conservation of momentum, which states that the total momentum of a system or group of objects remains constant if no external forces act upon it, and can be represented by the several equations and formulas you see below. By the end of the video, we'll be able to both visualize the conservation of momentum in a true elastic collision while understanding the motion of an object in an observed inelastic collision. To generate an observed model of the conservation of momentum, I used an aligned rule of 3/4, of which I then flicked a fourth quarter labeled coin mass A into one end of the row, which results in the quarter on the other end labeled coin mass B being ejected from alignment seemingly at the same velocity and motion of coin mass A. I then used the data analysis software tracker to generate an observed model of the motion of coin mass A going into the row and the coin mass B coming out of it. And then, to make things interesting, I repeated this procedure using pennies instead of quarters as the object of my system to compare. Moving on to my GlowScript computational code, as always, we must start by establishing initial conditions. That being my system being the line of quarters, my surroundings being the table, its mass being 5.67 grams, and the initial velocity being 0.96 meters per second. Also, I wrote a line of code noting that the quarter's momentum is its coin's mass times velocity. Then I simply modified this while loop you see here to include the iteration of momentum using the velocity as well as the momentum update formulas. And once again, I repeated this procedure using pennies and their respective initial values and conditions. While the GlowScript models exhibit similar or even identical models for momentum of the coin masses A and B, my observed tracker models do display some variation that leads me to believe that true momentum conservation was not observed here. This, I reason, is due to the fact that truly elastic collisions don't exist in nature and that some energy of motion was likely dissipated through an external force such as friction. Possible errors in my procedure of this lab may arise from slight miscalculations of initial velocity of the coins or misguided or inconsistent tracking of the coin's point mass when using the tracker software to generate my observed models. So what if the mass of coin A was different than the mass of coin B during the collision? If this were true, then the resulting momentum would be the sum of coin mass A and coin mass B multiplied by a new velocity. And what does it mean for the velocity of coin mass A to be equivalent to that of coin mass B if the masses A and B are equivalent? So this basically means that 100% of the momentum was transferred and conserved during the collision, meaning that it was truly elastic. Thank you so much for watching, and I hope you enjoyed.